today I'm going to talk about the reproducibility of structural MRI. And that's actually a pleasant thing to do because, as it turns out, structural MRI is a rather reproducible phenomena. It's actually the most reproducible phenomena I ever looked at. And so what I always try to tell to my students is that in psychology, we have two important research traditions. The first tradition is that of the experimenters. In this particular case, we try to manipulate a variable and find out if that has an effect. Within this tradition, we usually have a treatment effect that is found at time point 1, and we want to make sure that that treatment effect is significantly different from 0. And we also have a treatment effect at time point 2, and that should also be significantly different from 0. So it's very much focused on a significance test, that tradition. We also have a different tradition that very much focuses on correlations. Those people are therefore called the correlators. And what they want to do is to focus on the individual differences as they occur in populations. So they're not necessarily doing manipulations, but they rather look at the distribution of a particular phenotype and see whether they can somehow correlate that with other phenotypes. And within this context, reproducibility exists when the individual differences between people are conserved at time point 1 and time point 2. And it's usually expressed, which is no surprise, as a correlation. And tonight, we are looking at reproducibility within the context of correlations. Now, our phenotype tonight will be the little gray cells we all know from Hercule Poirot. And so the gray matter is found here at the outer part of the brain. It's where the actual neurocognition takes place. So that's where the actual computational things are happening. And we see the white matter that mainly consists of fatty tissue, and it's connecting the gray matter with other centers in the brain. And it's therefore rather similar to the telephone cables we once had in our homes. So we can, this is of course a very beautiful image of white and gray matter, but it's unfortunately a post-mortem brain. Unfortunately, we can now also make these kinds of images with structural MRI, albeit at a much lower resolution. So here you see the white matter as it is obtained in MRI, and you also see the gray matter. So the border of the white matter is here reconstructed with that yellow line, and the border of the gray matter here is reconstructed with the red line. And as you can see here, probably, I'm not quite sure whether you can see those, but there are 3 small green arrows that show how thick the brain is at that particular case. Now, usually the test retestability in structural MRI or a functional MRI is estimated across individuals. And I've tried to give you an impression how that is done. It's a little bit strange maybe, but suppose we have a brain here in subject 1 that is measured at a test session, and we measure that very same individual also at a retest session, let's say a month later. Then we can observe how thick the cortex is at a particular point at the brain. And in this case, for this individual, it's 2 millimeters, right? Now, for subject 2, we can do the very same thing. In this particular case, subject 2 has a cortical thickness of 1 millimeter here, and in the retest session as well. And we have finally the subject 3 that has a little bit more thicker cortex. And in this particular case, it's 3 millimeters, both at the test and the retest session. And the reproducibility is now estimated by correlating those 3 values across individuals. So this very simple graph tells you that indeed in subject 1, it was 2 millimeters balls at the test and the retest session. In subject 3, it was 3 millimeters balls in the test and research test session, and so etc. So the group reproducibility is usually estimated across individuals. And when we do this, we follow a strategy that was once pushed by my former boss, who was a psychologist, but also a mathematician, a little bit like John, so I have a preference for those people. And he suggested to do this with the intra-class correlation. That's a little bit different from the normal Pearson correlation. So in the normal Pearson correlation, we have X, that is, so to say, the mean of one measure, that be body size. And we have Y, which is the mean of another measure, that be body weight. And so we have, so to say, two distinct means that are used, which is, of course, logical, because looking here at two distinct quantities. But in the intra-class correlation, we have the same quantities. Let's say we're now talking about cortical thickness. And then it is possible to pool the means of the X and the Y. So the correlation has a little bit a different shape. You can see it here. So we use the pooled mean to estimate the correlation. And another pleasant side effect of the intra-class correlation is that we can correlate several observations of several individuals. So it's not restricted to two, but we can have, so to say, more observations. So that's the pleasant thing of the intra-class correlation. And we will make a little bit use of it later on in the small speech. So this is the normal group reliability as it is always executed. And we indeed see that the test retest reliability is rather high. I've thresholded it here at 0.75. I mean, there is this guy in psychology, his name is Cicchetti, and he claims that everything higher as 0.75 is superior test retest reliability. And so we see indeed that the largest fraction of the brain shows rather impressive test retest reliability. There are regions where the test retest reliability is a little bit lower. There is here in the central sulcus, where the motor and the sensory aspects of the human behavior are coded. Also a little bit here in the planum temporale, which is closely related to the hearing centrum. So it's a very important part of the brain. And here in the more inferior part of the insula, we see also a somewhat lower reliability. And of course, here in the sulcus calcarinus, I'm not quite sure whether I can have it. Yeah, here is the sulcus calcarinus. Also somewhat lower reliability, but overall, the thing seems to be rather high. Now, you could, of course, question whether such a group reproducibility has any clinical relevance. I have small doubts, but I'm not quite sure. So here we're looking at the brain where we see a tumor arising. And if you are a doctor, you're of course not interested in, let's say, group reproducibility, but you want to know whether those specific regional anatomical features can be reproduced. So for instance, we see here this white line that encapsulates the tumor. And of course, as a doctor, you would rather know, can I reproduce, so to say, these aspects of neuroanatomy within a single subject? Because that's the only subject of interest. And I try to come up with an idea that stems from an older paper of mine. So the basic idea is that you have a surface, and on the surface, the cortical thickness is projected. Now, suppose you have this very small surface here, it's called the region of interest, then it is possible to extract the cortical thickness within that region for the 40 individuals that were studied. And in this particular case, every single line you see here refers to a specific individual. So the vertical line is the cortical thickness, and the horizontal line is the position in space. And we see that the cortical thickness profile for the 40 individuals in the study is rather similar. What we can do is cross-correlate all those people, and we get then the average similarity, so to say, if you average it. And it tells you how similar human beings are with respect to cortical thickness. And we see that it is very much the case in the central sulcus, and to a lesser extent in the ventral aspect of the, the insula, right, the insula. Okay, so the idea now is that we don't correlate distinct individuals, we can also correlate an individual with itself. And what we don't get is, of course, test retest reliability. So instead of having 40 lines, then we would only have 2 lines, a cortical profile of an individual at the test, and a cortical profile at of an individual at the retest session. And that would be then our within subject test retest reliability measure that can be informative for just one single individual. Now, if you do this, we have 99 individuals. Then you can, of course, create 99 maps. That's quite a bit of maps. So I had the idea to start with the person that exhibits the poorest single within subject reliability. So now this is an individual that shows really not that great test-retest reliability. I've thresholded the maps at 0.6, which is good reliability, but you see, yeah, this person doesn't achieve that in the most part of her or his brain. I will now push on the button and we will see how these single subject maps differ from individual to individual. And so here you see it, and I hope that you appreciate that the test-retest reliability of the individuals is quite different from case to case. So not everybody has high test-retest reliability in the same parts of the brain. And so this is a little bit, I'm not sure whether you call it disturbing, but what I want to say here is if somebody has high test-retest reliability, let's say in the parietal cortex, that does not automatically mean that other people have high test-retest reliability in the parietal cortex as well. So there is a very substantial difference between individuals. The good message here, though, is that the test-retest reliability at a single subject level is nonetheless quite high. So it's nonetheless quite substantial. So there are altogether 99 maps. I'm not going to show you all of them because at the end of the day, they will be mostly red. So I stopped it here, but you get the smell of what I wanted to say. So I'm always a little bit a fan of Winnie the Pooh, and I always love how the titles work, in which Pooh and Piglet go hunting and nearly catch a woozle. Now, we're not going to catch woozles today. I'm hoping to catch test-retest reliability, and so I've changed it a little bit, and it's now the question is in which meta-reliability is introduced and questions are raised. Now, what is meta-reliability? I really don't know it myself so well, but I refer to meta-reliability as the reliability of the reliability maps. So something that is, so to say, an extra layer of reliability. So suppose we have one subject with one test-retest reliability map, and we have a second one, and there's also a test-retest reliability map, and we have a third one. And in principle, we can correlate the within subject test-retest map of subject 1 with that of subject 2, and subject 1 with subject 3, and so on and so on. And what you get is the across subject reliability of within subject reliability maps, right? It's a little bit abstract, so just take a little bit of time. So the question here is, if somebody has a high test-retest reliability, let's say in the parietal cortex, would that then be also the case in the other ones? And that you can do by cross-correlating all the within subject maps across individuals. And if you do this, then you get this histogram. This histogram tells you a little bit how similar the test-retest reliability maps across individuals are. And as it turns out, it's not that high. It's roughly around 0.3, which is, yeah, not that high. You can do that a little bit more formal test. So you can put the 99 maps that I have developed into an intra-class correlation, because the intra-class correlation actually allows you to correlate a lot of individuals at the same time. And then the meta-reliability is roughly 0.25, which is not too high. Now, what you can do, of course, we have 99 single subject reliability maps. You can construct the mean map. And so one prediction that John actually made turned out to come true. So John said that the group reliability and the mean within subject reliability map should be somehow similar, and they are, right? I will show you later. So if you average the single subject maps, then they turn out to be rather similar to the conventional group reliability. What we're seeing here indeed again is that we have a rather low reliability in the central sulcus, Also here in the cingulum, the superior temporal sulcus, and last but not least here in the temporal parietal junction. So it's a pattern we have also seen a little bit in the group reliability analysis. Now, the nice thing about the single subject test retest reliability maps is that you can estimate the standard deviation of those. So you can see where the largest differences in test retest reliability on the single subject level are found, and we see actually a rather consistent pattern occurring. It's along the dorsal stream of the brain. So if you look at the most superior part of the brain, you will actually see that, oh, here it is, excuse me for it. So if you follow the dorsal stream of the brain, you will see that there's a higher, let's say, variability in test retest reliability if whether we would compare it to the more ventral stream. And why that is the case, I don't know, but you see this part of the brain is much greener, and even in the inferior frontal, that's the case. But if you look here at the superior parts of the brain, the variability is much higher. So I'm not quite sure whether that's the case, but it's something we can observe. Now, here is what John actually predicted, and it sort of turned out to be the case. So this is the conventional, at the left, you see the conventional test retest reliability maps in which we correlate across individuals. And on the right, oh, excuse me, you see a average map of 99 single subject test retest reliability maps, right? So this is the average. And if you compare the left with the right, indeed you see that the blue parts are found on similar parts of the brain. And you can actually correlate those two maps with each other. And what you then see is that the correlation is indeed substantial. It's 0.74. So we see indeed that there is a similarity between those maps, although they have been constructed in a rather different way, right? So nonetheless, if we start to correlate the single subject test retest reliability maps with the group reliability maps, we see that only a modest correlation is found. It is not that it is absent, so it's around 0.4. But yeah, it's difficult to say because we have a specific group effect, and let's say in the parietal cortex, let's say we have a high test retest reliability in the parietal cortex. This does not automatically tell you that all people in the parietal cortex have a high reproducibility at the single subject level. But it is also not the case that there is nothing in it, right? So it's just somewhere in the middle. So I would like to draw some very preliminary conclusions. So MRI is reproducible both at the within subject level and the group level. The meta-reproducibility on the within subject level is rather low, right? We cannot say because somebody has a high reproducibility in one map that it is then automatically the case for somebody else. The group reproducibility maps and the mean within subject reproducibility maps show high correlation. So they are nonetheless, so to say, tightly connected to each other. And then finally, the within subject reproducibility maps have only a modest correlation with group reproducibility maps. So we can, so to say, group level findings cannot be directly inferred to the individual level. And I think in philosophy, they call this ecological fallacy. So yeah, I'm somewhat puzzled, but also pleased with the results. So yeah, they're very fresh, so I don't really know what to make of it. So my feeling is maybe it's better in the future to produce mean within subject reproducibility maps, because you can then also have the standard deviation. And you get more information about the variability of reproducibility. And I'm not quite sure if we should report meta-reliability. So yeah, that's what I have tried to do the last weeks. And yeah, I'm happy to report, to respond to you. So that's it for now.